So we'll start talking about learning from limited label data, few-shot learning in particular for medical image data. And then, depending on how much time we have, we'll continue talking a little bit also about explainability. And both these topics in common in this presentation and this tutorial will have prototypes. So they're both building on the idea of prototypes. And what that is, we'll get back to in a second. So first of all, medical imaging, medical image segmentation. Of course, there are a lot of different challenges when we're trying to work with medical image data. And two in particular are this learning from limited label data and explainability. So in general, when we have some data, medical data that we're looking at, usually we don't have a lot of labels because medical experts need to go in, annotate, especially in a segmentation task. They need to annotate every single pixel. This is very time-consuming, very expensive. They usually have better things to do. But we also might be in a setting where segmentation, where the labels can be quite subjective. So different medical experts can be disagreeing on what is the correct label here. And the other part, the explainability part, here we are trying to design methods which ideally can be used in practice, used by medical practitioners. So when they want to use the models, it's not enough that the model just says, okay, this is whatever disease or whatever outcome they're interested in, but they also want some explanation of why the model thinks that this is a particular disease, for example. So these are two key challenges in medical image segmentation or medical image analysis in general. So, as I mentioned, we'll start by diving a bit into few-shot medical image segmentation. And the general idea or the general concept or the general approach when you have a new medical problem is to collect a lot of label data and train it in a fully supervised manner. So you have some data, you collect a large data set where you do have the ground truth, you do have the annotations, and then you provide the data to your model, the model produces some output, you compare this output to your labels, compute some loss, and then update your model. And this works nice if you have these large data sets, but if you only have a few examples, this usually doesn't work well. So this is where this idea of few-shot segmentation comes in. So the few-shot problem has been studied quite a lot, especially outside the medical domain. So, and most of the work has been focusing on classification. So the idea is, okay, let's assume we have some known classes, so some classes where we do have a lot of examples of. So for example, in this case, we have the person class, the chair class, the cat class, and the dog class. So these are our so-called seen classes. And then we have a set of unseen classes, so classes where we don't have a lot of examples. So in this case, the shark, the bike, the plane, and the horse. And what we now want to do is we want to design a model which can be trained on the seen classes, but then generalized to the unseen classes with only a few examples. So this is the idea of few-shot, few examples in order to generalize to new classes. So the idea is train a model on our seen classes, and then once we've trained it, freeze that model, and then leverage the unseen classes, some examples of the unseen classes, or few examples, in order to do inference on the unseen, or the unseen classes. So how can we do this in a segmentation setting? So the natural approach of doing this is to say, okay, we have our neural network, some classification network. We can cut off the end of it in order to just use it as a feature extractor. So we take our image, so-called our support image. Yes. So we have a support image, which is just from the seen classes. We take an example of an image and the corresponding ground truth. We send the image through the feature extractor, get a bunch of features for the different spatial locations in the image, and then we have our ground truth mask. So what we can do is we can sort the feature vectors into foreground and background class. Once we have done that, what we can do is we can compute prototypes. So these are kind of representative features for the different classes. So we can say that, okay, let's take the background feature vectors in this case, compute a mean, that's our prototype for the background, and similarly we can do the same for the foreground. We can take all the foreground features, compute a mean, and we have a mean, or a foreground prototype. Once we've done that, we can take another image, in this case another image from our scene classes, where we do not, or where we assume that we do not have the ground truth mask. So what we do is, we send it through the network, the feature extractor, get a bunch of features, and then we assign the features to the closest class prototype. So we can say, okay, this feature, if this feature is closest to the blue class, it's assigned to the background, otherwise it's assigned to the foreground. That way we can segment this query image, and then since it is from the scene classes, what we can do is we can compare it to our ground truth, that way compute a loss, and then train this feature extractor. And this feature extractor is just the same, so it's just shared feature extractor. So this is what we can do with the scene classes, but now we want to generalize this to the unseen classes. And the idea here now is that what we can do is we can take our unseen classes. We do have a few examples for our unseen class. So for example, let's just assume we have one single example of the shark class, for example, in this case. So what we can do is we take our shark image, send it through the network, get the features based on the ground truth for this one example. We can compute our class prototypes, shark prototype, background prototype, and then we can do the same. We can take our unseen query images where we do not have the corresponding ground truth, send it through the network, assign the features to the closest prototype, and that way produce segmentation results for classes which the model has not seen during training. Does that make sense? Yes, perfect. Okay, however, now what we want to do is we want to move away from the kind of natural image domain where we have a lot of labeled examples, a lot of classes where we have many labeled examples, and instead we want to move to the medical few-shot segmentation. And one particular setting here, or one particular case, is that in the medical domain we usually don't have these vast amount of scene classes. So, for example, in the natural image domain you would use the ImageNet dataset, you have 1,000 scene classes, but in the medical image domain this is often not the case, and you do not have vast amounts of labeled training data. So how can we address this? So in general, when you have settings where you do not have a lot of training data, one thing that comes to mind is self-supervised training. So how can we train a model without assuming or without requiring labeled data, but still have a model which kind of extracts useful features? So self-supervised training. What is self-supervised training? In general, the idea with self-supervised training is that we want to learn a model which learns some useful features without requiring annotated training data. So the idea is that we want to design some form of task where we can, for free, generate labels, and when the model tries to match these images to the labels, it will learn some useful property or some useful features. And just to illustrate this, what we have here is we have a model. We take an image and we can transform the image. So we can have our image of a dog. We can transform the dog image, so we can just flip it sideways. And we know that, okay, this is still an image of a dog, but now it's a dog image which has been rotated. So in order to learn useful features in the encoder, we need to figure out a way of designing a task so that the model still needs to understand, okay, this is an image, or it needs to understand how to extract useful features of the input image. So what we can do with the dog is we can say, okay, we rotate the dog, and then we try to predict how much the dog has been rotated. So in order to predict how much the dog has been rotated, the model needs to first figure out, okay, what is the object? how is this object usually rotated? And this way it's kind of forced to extract useful features in order to solve this kind of completely irrelevant task. So we're not really interested in predicting rotation, but we are interested in what happens here, this encoder, what features are learned, so that based on the features we can predict the rotation. This is one way of doing it. The other way of doing it is to say, okay, we have some input image, we transform the image, so again, it could be some rotation, we send it through the same encoder, the same feature extractor, and then we say that the representations, so the features that you get, should be as similar as possible. So they should be consistent, because if we have a dog and we rotate the dog, it should still be a dog. So the representation should be invariant to rotation. And this, of course, generalizes from not kind of beyond rotation. You could choose various different tasks. However, in this case, what these tasks are doing, they are trying to do this on an image level and not a pixel level. So in this work, we are looking at image segmentation, medical image segmentation. So what we want to do is we want to do this on a pixel level and not. So we want to learn some task or design some task which can work on a pixel level and not on a full image level. Because we don't want a representation for the whole image, we want a representation for the different spatial regions in the image. So one way to do this, and this is some work which was presented at ECCV back in 2020, was to build on this notion of superpixels. So the idea here is that we can use superpixel algorithms to find regions in the image which are roughly similar. So you can take an image, you can compute the superpixels, and what you will get is something like this, where you kind of group similar pixels and together, which are in close spatial proximity. What we can then do is we can sample one of these superpixels, and we can say, okay, now this is our ground truth for this image. So we have this image, we get the superpixels, we sample a random superpixel, and then that's our ground truth. That's our support, and then we can apply some transformation, could be rotation, could be some intensity modification in order to get the query example. So now we have our support and our query, and we can use this same idea that we saw previously, where we can take our model, send the image through the model, get the features, sort them based on our ground truth, get our foreground background prototype, and then use it or use those prototypes to segment the query and then compare it to the query ground truth in order to get a loss and that way train a feature extractor. And note here, we're not using any labeled data, right? The only thing that we do is we generate labels based on the superpixel algorithm, which is completely unsupervised. In the medical setting, we're often interested in looking at 3D objects. So for example, in this case, we're looking at MRI images, and we are interested in trying to segment out different organs. And what we can do is we can generalize these tasks from superpixel segmentation to supervoxel segmentation. So instead, we can take this image cube, we compute supervoxels. So now each region here is kind of a 3D object. And then we can sample, as we did previously, we can sample a random super voxel. And then instead of taking the same slice and performing some augmentation, what we can do is we can, since it's a 3D object, we can take different slices that kind of contain the same 3D object. So for example, in this case, we can take 2 different slices which contain this particular super voxel. And this is what we see here. And of course, then in addition, if we want to, we can apply some form of transformations. Okay, so this allows us to train or kind of circumvent this first problem of not having a huge amount of labeled training or labeled training examples from scene classes. However, another thing which is commonly encountered in the medical domain when you want to do segmentation is that you are interested in some particular region of interest, which often is relatively homogeneous, but then you have a lot of other stuff, other organs and so on in your image. So generally what you'll see is, if you take your 3D scan, you have one organ that you're interested in, and that organ is relatively homogeneous, but there's of course a lot of other organs, which means that you have quite an inhomogeneous background. And yeah, this is just to illustrate it. We might have one organ of interest that we're looking at, but then we have a lot of other stuff, and you can see, imagine this kind of all across the body. There's a lot of other stuff in the body, organs and things like that. So what people would usually do is they would follow this approach that we talked about previously. So they would take the data, embed it, sort it based on the foreground and the background, and then compute some prototype. And since you have this large inhomogeneous background, it's usually not enough to just have a single background prototype. So what you could imagine is, let's have our foreground prototype, which is just a single prototype, but then generalize this idea of having the background by having many different background prototypes. The problem with this approach is that, first of all, you don't really know how many background prototypes you might need. This is quite arbitrary. Some previous works have said, okay, let's choose 256. Why not? This means that, first of all, they need to be, you need to choose this arbitrary number. And then also when you want to do inference, so when you have a new example, a new data point, a new spatial location in some query image, what you have to do is you'll have to compute all these distances to all these 256 different prototypes in order to find the closest prototype and then assign that pixel to it. What we propose in this work is to instead say, okay, let's just avoid modeling this background because it is inhomogeneous and difficult to model. So instead, let's just say, okay, we only care about the foreground and we only model the foreground. So we say that, okay, we have some foreground prototype and we want to learn some notion of a threshold so that we can say that points or samples which are close to this foreground prototype should be classified as foreground, and otherwise they should be classified as background. So given a new data point, the only thing we have to do is we compute the distance to the foreground prototype, and based on that we make the decision. Putting this together, what we can do is we can design a framework. In this case, it's called the ARDINET, anomaly detection-inspired few-shot medical image segmentation. And the idea here, going all the way back to how, how you kind of, in a normal way, do few-shot segmentation. You take your support, you send it through the encoder, you get your features, you assign your features based on the segmentation mask for your one or two or whatever few query examples or examples from the unseen classes. And then you compute your foreground prototype, and then your query example you send through the encoder. You don't have the ground truth, so you just get the features. And then what we do is we compute negative cosine similarity to this prototype, and then learn threshold t in order to distinguish foreground from background. And here, this t is just an additional parameter in the model, which is learned during training. So now we, based on our kind of generated training data, we can compute a loss and then backpropagate and learn both the feature extractor but also the optimal threshold. So this, combining it with the self-supervised approach, we have during training, we have our supervoxels. We select one supervoxel which we consider as the foreground in this, or for this batch, or for this sample in a batch. We select two slices that cover the same supervoxel, potentially apply some form of augmentation, and then send it through the model. We have our ground truth, just the super voxel that we've selected, and based on that we can compute the loss and train the model. And then during inference, we then take a new volume. We know which class we're interested in, so this is the one example, for example, of the scene class. And then we, based on this segmentation mask, we can compute the foreground prototype, and then we can send the query volume or query slice through the trained ADNet model, and then just compute distances to the prototype, apply the threshold in order to get our prediction for the unseen class. If we do this and we kind of compare to prior approaches, especially these approaches which were using a lot of different background prototypes, what we'll see is over here. Before I talk about the results, just some information on how these models are usually compared. So previously, at least, what people were doing, especially in order to avoid this effect of this inhomogeneous background, was to say that, okay, we want to segment some organ. We know where the organ is, so we can say that, okay, let's divide the organ in the support into 3 different slices. This gives us 3 different support slices. And then we also assume that we know where the organ is in the query image. And if we do that, we can then say, okay, let's use this slice in order to segment this region, this slice, so the orange slice, to segment the orange region, and so on. This assumes that we know where the object is in the query setting, but in practice, you're interested in segmenting the organ in the query image, right? So you don't necessarily know where the object is beforehand. However, if we follow the same setting, what we generally see is that this ADNet performs roughly similar to especially this ALPNet, which is this model which was using 256 prototypes all over the background. If we now generalize the setting, and we say that, okay, now we just assume that we have one support slice, and we want to segment the full query volume. So now we don't make any assumption of where the organ is. If we now just apply this one single support slice in order to segment the full query image, what we'll see is that previous approaches degrade significantly because they don't, they are not able to handle this inhomogeneous background. So what you see is that while ADNet degrades a little bit, it's a much more difficult task, you can see that performance of previous models degrades considerably. Also, since we have this 3D self-supervised task, what we can do is we can generalize this to 3D, use 3D convolutional neural networks, and so on. That way, further improve performance and get to something which was similar to previous approaches without having to require this, these weak annotations of where the organ is. So this is just this first part. So now we have a model. We have this ADNet, which can, based on just a few labeled examples, segment new classes. And it doesn't assume that we have a vast amount of labeled data to start with. So it's trained, the training is completely unsupervised, and then inference just requires 1 or 2 or 3 examples in order to perform segmentation. However, there are still problems with this approach, and some of these are listed here. So one is that in this work, we're focusing on this idea of binary segmentation. So we're just looking at one foreground prototype, and then the rest was considered the background. Also, what you might notice, especially if you look a little bit closer at the results, what you often see is that there is this imprecise boundary around the organ. So it's not able to precisely model the boundary of the organs. And finally, a bit related to this imprecise segmentation, it also doesn't provide a notion of uncertainty, which can be quite useful in medical settings. So let's start from the top and see how we can, given that we have a trained ADNet, how can we address these problems. So starting with the binary setting, what we would usually do is we would take our ground truth, so the ground truth for the particular example that we have, so our few examples. We compute a foreground prototype, and then we assign the query feature vectors based on the distance to this prototype. And this is what we see here. If we now want to use it to also segment another class, what we can do is we can compute the prototype for another class, so in this case the spleen, and again we can assign points based on the distance to the foreground prototype. However, as you might notice, this leads to these ambiguities where now some query feature vectors will be assigned to multiple classes. So what we want to do is we want to resolve these ambiguities, and one way to do this is to generalize this to a multi-class setting, where you now say that, okay, we have multiple foreground prototypes, and if we have data points which are in this ambiguous region, we just assign them based on the closest class prototype in order to resolve the ambiguities that we have otherwise. Looking at this in practice, especially, so in this case, we were looking at cardiac segmentation, so segmentation of the heart. What we can see is that in this case, we have three classes which are quite close to each other, which are bordering each other. And what you can see in the binary setting is that you get a lot of over-segmentation, where some region is assigned both to the red class, but also to the green class. Doing this in this multi-class segmentation, you're able to resolve this and ensure that you now only have assign each pixel to one particular class. Showing this or evaluating this qualitatively, we can also see that, okay, doing this improves performance significantly compared to the original RDNF model. And here we are not doing any retraining, this is just doing inference, just addressing these problems from an inference perspective. I also mentioned this problem of imprecise segmentations, and this is what we can see here. So here on the left, we see the ground truth. It's generally quite, it's the ground truth. And then we have the prediction, and we can see that, especially in the boundary regions, it's a little bit blurry, right? It doesn't follow precisely the boundary of the organs. So how can we remedy this? And in order to do this, we can think back, okay, what follows boundaries relatively precisely? That's supervoxels or superpixels. So the idea now is that we already compute supervoxels for our support images, but we can also compute supervoxels in the inference phase. So we can take our image, we compute supervoxels, and then we embed our image in this feature space, and then we say that, okay, points which belong to the supervoxel, same supervoxel, should be somewhat similar. So we propose this feature refinement, where we just say that, okay, feature vectors which belong to the same supervoxel should be compacted. This way, we get this kind of disentangling effect where, for example, in this case, the feature vectors get kind of pulled towards the center of that supervoxel and get disentangled. And this is just done by this combination of, so we compute the mean of each supervoxel, and then we have this beta which trades off how much feature vectors are supposed to be pulled towards the mean. So if we have a beta of 0, so this is the original feature vector before the refinement. If we have a beta of 0, it just means that the feature vector would be pulled all the way to the mean of that supervoxel. And if we have a large beta, it just means that we don't do that much refinement. Looking at the architecture for inference, what does that mean? Okay, the thing that we can do is we can do the supervoxel refinement, feature refinement here, by having some beta, which defines, okay, how much refinement do we want to do. And just to illustrate what the beta means, I already mentioned, so putting beta equal to 0 means pulling everything towards the supervoxels. So you can see, of course, this follows precisely the border of the supervoxels, but yeah, it can be a little bit too rigid. So usually you don't want to pull it all the way to the supervoxel, but you want to choose something a little bit more intermediate. But this means that we need to find some good beta value, right? Because we're just kind of moving this problem of, okay, how do we select a good beta value? If we, for some reason, know some optimal beta value, we can say, okay, we can improve. But how do we choose this beta value? One way of choosing this beta value would be to do some form of line search. However, in this case, we don't really have labeled data, right? So we can't really do a line search. So instead, are there some other ways of finding this beta instead? So what do we know about boundaries, and what do we know about these kind of blurry regions that we want to improve upon? We know that these blurry regions, boundaries, they are there because the model is most likely uncertain about what the correct label is for this particular feature vector. So let's try to incorporate uncertainty into this and say that, okay, let's refine feature vectors which the model is uncertain about more than feature vectors which the model is certain about. So this means we need some mechanism of computing uncertainty, and since we're just looking at the inference phase here, we need some architecture agnostic mechanism to compute uncertainty. And the way we can do this is we can consider the masked average pooling, which we're doing. So we compute the features, and then we do this masked average pooling. We'll compute the prototype. Instead of doing the masked average pooling, what we do is we introduce a Bernoulli mask in order to introduce randomness. So we have this masked randomized average pooling, and then we can sample multiple foreground prototypes, and we get this distribution over the foreground prototypes. So our updated model now looks as follows. Again, we have our support image, send it through, and then we do this masked randomized average pooling instead of the masked average pooling. We compute multiple prototypes, so samples of this distribution over the prototypes. And then we can compute the uncertainty by looking at the predictive entropy over all these different samples of our, over the distribution of our prototypes. And we can use the mean over these as our prediction. So just to visualize this again, so we have our images, we have our ground truth, we have our prediction, and then we have our uncertainty estimates, and we can generally see that bright pixels mean high uncertainty, so we can generally see that in these boundary regions we do get high uncertainty, so it kind of corroborates our intuition that these boundary regions are generally the uncertain pixels, and that's why we get these blurry results. So let's replace the beta with our uncertainty. So let's say that, okay, our beta should be 1 minus the uncertainty estimate for this particular super feature vector. So we now just replace our beta by 1 minus u, and then we now don't need to choose a beta, we just choose it automatically based on the uncertainty. And if we do this, so without having to select a beta, we can see that we're actually able to get results which are relatively similar to selecting the best beta, just that now we don't need to choose it, and it can be done in an unsupervised manner. This can, of course, also generalize to various other settings, so we can go beyond organ segmentation and kind of cardiac segmentation. So, for example, this can also be tested on images of the brain. So, in this case, ischemic stroke lesions, trying to find ischemic stroke lesions in the brain. And this is more just kind of tailoring of this method, where now you generate the supervoxels not directly based on the images, but some meta information that you can extract from the images. So just to summarize this first part, let me just have a look. There's still time, okay. Just to summarize the first part. So here we looked at a framework to do medical few-shot segmentation, building on ideas of self-supervision and this idea of only modeling the foreground prototype and not the background. And we've leveraged supervoxels in order to do this boundary refinement and leverage a notion of uncertainty in order to control how much different areas in the image or in the volume should be refined. Then we have a little bit of time to dive into data bias as well. So here we are still in the medical domain, and now we are looking at some investigation of data bias and data imbalance in the medical setting. And in general, when you are in this learning from limited label domain, what you often do is you take data, all the data that is available, all the data which is labeled, you pull it from different hospitals, different whatever you can get your hands on, and you try to leverage that. However, there is a problem, and what we'll see here is that if your data has some form of imbalance, and surprisingly little imbalance, the model often starts to exploit this imbalance in order to cheat a little bit and improve the results. So here the setting is we have data from multiple hospitals, 2 different hospitals, and we consider this case where the data is imbalanced. So for example, one hospital might specialize on certain patients and that way have considerably more patients of a certain type. So in this investigation, what we did, we considered this task of pneumonia detection, so trying to figure out does a patient have pneumonia or not. And just to illustrate this problem with imbalance, we trained a set of 11 models. So each of these points here on the x-axis corresponds to a trained model. So what we see is, or what this first point means, is that, so we have 0% of pneumonia images from hospital 1. So that means that whenever we train these models, we always train them balanced, so we have the same amount of images from hospital 1 as we have from hospital 2. But in this case, 0% pneumonia images from hospital 1, that just means that all the images that come from hospital 1 are non-pneumonia images. And similarly, 100% of pneumonia images from hospital 2, it just means that all the images from hospital 2 are of patients that have pneumonia. So this is kind of the extreme case, right? And then we vary these percentages all the way until we now have 100% of the images from hospital 1 of patients with pneumonia and 0% of the images from hospital 2 of patients with pneumonia. And then we evaluate the performance on a set of testing data sets. So one where we have 100% of pneumonia images from hospital 1 and all the images from hospital 2 are non-pneumonia. This is just the opposite. So now all the images from hospital 2 have pneumonia and all the images of hospital 1 of patients that do not have pneumonia. And then we have this perfectly balanced setting where 50% of the images from both hospitals are pneumonia and the other 50% are non-pneumonia. And if we look at these curves, so the curves correspond to the different test settings or test splits, what we can see is that, okay, if we have a model which is trained in a very imbalanced way, and we test it on an equivalently imbalanced data set, of course, we get good performance, 100% performance. If we instead test it on the test split where these kind of fractions are split or inversed, we see that the model performance is 0. So we kind of have these regions where the model is just learning where the image comes from, so which hospital does the image come from, and not really picking up on if the patient has pneumonia or not. And similarly, if we look at this kind of 50-50 split, we see that, okay, initially it's just 50-50 because it's only looking at where the hospital, which image comes from which hospital. But then as we approach this kind of 50-50 split, also during the training, we get more reasonable performance. And if you have data from two different hospitals and you have a lot of data, then of course you can do something like this. You can do a study like this and you can analyze in kind of a synthetic setting, okay, how do these curves look? But in most cases, we don't know these fractions beforehand. We might not have enough data to actually try all of these different combinations. So what we want to do is we want to use some different way of figuring out what is the model focusing on. And this is where this idea of explainability comes in. And the idea with explainability, I mentioned it previously, is that, okay, we have some model, takes an image, gives us some classification, and then we have the prediction, but we don't really know why the model comes with a certain prediction. Instead, what we want, or what people have been working towards, is so-called explainable models. So we have an image, we get the prediction, and then we get some form of intuition of what areas in the image are relevant for this prediction. And there are various different ways of visualizing different types of explanations, but this is one way. So so-called kind of heat maps where you have red pixels indicating areas in the image which correspond or positively affect your class prediction. And the different approaches for explainability, they've been kind of going in two different directions. One is this idea of so-called post hoc explanations. So you have a model, it's trained, it's a nice classifier, and then you want some mechanism in order to, after the fact, explain why your model made a particular prediction. This is the one side, and the other kind of family of explanation methods is so-called self-explainable models, where you instead want to design a model which is inherently transparent. So you don't want to just take a black box model and try to explain its prediction, but you want to design a model which provides both a prediction and an explanation at the same time. And it can be argued that this is a preferable way of doing explanations, because here you're kind of guaranteed that your prediction and your explanation are directly linked. So one way of doing this, so just one self-explainable approach was proposed in this work from Neurops in 2019. And the idea here is that we have some image, we send it through our CNN feature extractor, we get our output features, so we have some spatial extent, so in this case 7 × 7, and then for each position we have a feature vector number of channels, in this case 128. And then we say, okay, we want to learn a set of prototypes, so just 1 × 1 × 128, so just a 128 vector. And we want to provide our predictions as in form of these prototypes. So we say, okay, we learn a set of prototypes, potentially multiple per class. We can apply these prototypes, or we can compute the similarity between these prototypes and each of the spatial locations in this cube. That gives us a notion of similarity of this prototype to each pixel. Then we can do some form of pooling, for example, max pooling, to just find the highest similarity. And then this similarity score we can use to as an input to just a linear layer in order to get our prediction. So then what you can do is you can say that, okay, this image is classified to this class because this class or this image has a high similarity to a certain prototype, which highly kind of contributes to this particular class. So you have, for each prototype, you get a similarity score, and you have the weight, which connects this kind of prototype to your class, right? So you know, does this prototype correspond positively or negatively to the individual classes? So this way you can kind of get an understanding in terms of these prototypes, how well do the what prototypes are relevant for this prediction and what do these prototypes look like. So there are various different ways of figuring out what these prototypes look like. One is just to find the closest feature vector in your training data, so you can run all your training data through this feature extractor and then compute all these similarities and then find the prototype or the feature vector which closely corresponds to your prototype. Or you can also extend this framework and potentially have a decoder in order to generate what these prototypes correspond to, kind of connecting to this whole idea of generative models, which we touched on previously today. Another thing that we can do is, for these models, we can, similarly to normal post-hoc approaches, we can generate these heat maps. And if we now go back to our examples where we have this very imbalanced data sets, so 90% of the images from hospital 1 were pneumonia, 10% of the images from hospital 2 were pneumonia, we can see that, okay, in order to figure out if this image is pneumonia or not pneumonia, the model is focusing on these particular regions here on the top, these textual annotations, in order to figure out, okay, which hospital is the image coming from, instead of looking at the lung area, which you would kind of assume that a good model, which is trying to predict pneumonia, would do. Yes, you can also look at the images which kind of correspond most closely to the different prototypes. But in general, what we see is that these models often, especially in this imbalanced setting, focus on trying to figure out, okay, what hospital is the data coming from? If we now go to this more balanced setting, so in this case 60-40, we can actually see that, okay, the model is starting to focus more on the lung, but it's still leveraging these tag informations in order to figure out which hospital does it come from in order to boost performance by exploiting this even relatively small imbalance. So it's not a problem which only happens in these extreme cases. It's something which you generally encounter quite a lot in practice. Yes, these are just some other examples of what the model is looking at. So often what you can see is that it's not only looking at textual annotations, but also at tubing and things like that. Here it's just an illustration of some method which was designed here in our lab, trying to improve these kind of blurry regions, the blurry explanations that you see in these proto-PNet heat maps, to get a bit more precise information of what actually is relevant for the prediction. So just to summarize this part, in general, if you work with medical data, and especially if you're in the setting where you combine data from different hospitals, one thing which is highly important is to figure out, is this data imbalanced? If it's imbalanced, you might need to take this into account, and you can't just take a model and train it on it, because what the model will do is it will exploit these hints of where the data comes from in order to figure out which hospital does the data come from and which hospital is more likely to have pneumonia patients or non-pneumonia patients. And also, in general, what I want to stress a little bit is that since you have these two directions, most of the work so far has been focusing on this idea of post hoc explanations, where you take a black box model and you try to explain the black box model. However, there is quite an interesting line of works exploring this idea of self-explainable models. So if people in the explainability domain are interested in figuring out some new direction, I encourage you to check it out, because there's still a lot of unexplored areas in that domain. Yes, and then I just want to thank my co-authors on these works. These four you will see around. Robert, you've already seen. If you want to discuss some of these aspects more, feel free to chat with them or ask questions now. And also Robert is available for questions now. And we still have some time for questions.